Hi class, I wanted to show you this supplemental example on terminal velocity. In class I talked about solving terminal velocity problems, and I said that there were three different ways to pick an expression for CD. So I'll write that: three ways to pick CD. The first I said was there was this big nasty expression as a function of the Reynolds number, and I said don't do that one. That requires the web. I mean that requires Python. That's fine to do, but it's more work than it's worth. The second I said was guess one, and I said this is the easiest way, and this is the one I recommend. So guess one, but don't forget to check the Reynolds number. Okay. And then I said there was a third way, which I called a smart guess. And I'm going to show you the smart guess. And the reason I'm going to show that to you is that some of you may feel kind of frustrated by this idea of just guessing and feel like you should have some intuition. And so I'm going to give you a way to sort of numerically calculate an intuition. But it involves a couple extra algebraic steps, and so it's just a supplemental case. So remember, we solved this problem for a ball, a baseball falling in air, and we said there was the buoyancy force, and there was a drag force, okay, and then there was the force due to gravity. And we wrote the force balance as follows. We said rho g volume plus 1/2 rho u squared drag coefficient projected area minus rho 0 GV. Okay, and this here, this is the object, or excuse me, that equals 0. So this is the gravitational force, this is the buoyancy force, and this is the drag force. Okay, so so what we did in class was I said let's just guess value for here. But if you want to do the smart guess, you have to do the following procedure. So the first thing that you want to do is you want to make the force balance dimensionless and rearrange a little bit. So what I'm going to do is I'm going to move some of this stuff over to one side and move this over to the other side. So let me just do a little bit of algebra here. Here, I'm going to scroll down to a little more space. So I'm going to come down here and do some algebra. So I have 1/2 rho u squared drag coefficient projected area is equal to rho 0 GV minus rho GV. All right, and notice that this I can pull out the GV and have rho 0 minus rho. And now I'm going to take this guy, and what I'm going to do is I'm going to leave CD over here. That's a dimensionless quantity, and I'm going to leave the u squared for a minute. So I'm going to leave u squared CD, and then I'll divide over here by 1/2 rho and the projected area. Okay, and the reason I'm doing this is I want to isolate on this side all of the stuff that depends on u. Okay, or i.e. the Reynolds number. Okay, all the things that depend on the Reynolds number are on this side, right? Because CD is a function of the Reynolds number, and obviously the Reynolds number includes u, rho u d over mu. Okay, so now I'm going to do a little bit of rearranging, and let me just grab the little notes to make sure I don't screw this up. Okay, so having done this, let me just rearrange a little. Okay, so I've got 2GV divided by projected area, and I have rho 0 minus rho divided by rho. Okay, now I can write down the projected area if I want, and the volume for a sphere, so that'll maybe simplify things a little bit. So the volume is pi d cubed over 6, and the projected area is the area of a circle, pi d squared over 4, and I can plug those guys in. So I'll give myself a little more space here. I have 2g, and then I have pi d cubed, let me fix that pi a little bit, divided by, and then that's over 6, then divided by pi d squared over 4, and then over here I still have my rho minus rho over rho, rho 0 minus rho over rho. Okay, and now the pi's cancel, and these d's go away, and I get a d up, just a single d left up here. And then the 4 comes in the top, so it'll be 8. 8 over 6 is 4/3. So now I'm going to get 4/3 GD, and now I have this rho 0 minus rho over rho. Okay, so this is just algebra I'm doing. And over here I have u squared CD. Okay, so now I look at this and I say, I want to make this dimensionless. I have u squared over here. What I'd really like to do is put a Reynolds number on this side. So to do that, I multiply both sides. I'm going to multiply by a rho squared times a d squared divided by a mu squared. Or another way of, okay, so I'm going to do that on both sides. So now I get rho squared u squared d squared over mu squared times CD. Okay, and over here I get 4/3, and then I have GD cubed multiplied by rho 0 minus rho over rho, and I have a rho squared over a mu squared. Okay, well remember mu over rho, that's equal to nu, the kinematic viscosity. So I'm going to have a kinematic viscosity in the denominator squared here, and this is the Reynolds number squared. Okay, so now I've made it dimensionless. Let me rewrite it. I have the Reynolds number squared, CD, equals 4/3 GD cubed divided by nu squared, and I have rho 0 minus rho divided by rho. Okay, now this quantity right here, this has another name. It's called the Archimedes number. Let's see, Archimedes number, okay? And the way to think about this is I can calculate this Archimedes number. It has to do with buoyancy and all sorts of stuff, okay? It's not important really what exactly the Archimedes number is a ratio of. But the important thing to see is that if this number is really big, okay, let's say if this number is really big, then I have Reynolds number squared CD equals big. That tells me that very likely the Reynolds number is big. Okay? Whereas if the Reynolds number squared CD equals small, then most likely the Reynolds number is small. So what I can do is I can calculate this thing over here, all right, and then solve for, and then using that I can guess which expression for CD I should get. So let me calculate the Archimedes number. The Archimedes number is GD cubed over nu squared rho 0 minus rho by rho. Okay, and now I got to look up the numbers from the problem. I didn't write them down up there, so let me pull them up here. So the numbers from the problem, we said that rho is 1.2 kilograms per meter cubed. Meters cubed. Rho of the object was bigger, and we said it was 630 kilograms per meter cubed. Okay, this rho, of course, is air. This is the fluid that the ball is falling in. The diameter of a baseball is 0.076 meters, 76 millimeters, and nu of air is 1.6 times 10 to the negative 5 meters squared per second. Okay, and without even doing the calculation, you can see that I have something that's 10 to the minus 5 in the denominator here, okay? And that's going to dominate. This rho 0 over rho is going to be around 600, but this is a small number. And at the end of the day, this is going to be order 10 to the 10, okay? Which means Reynolds number squared is on the order of 10 to the 10, which means that Reynolds number is on the order of 10 to the 5, which is exactly what we'll find, okay, which is what we did in class. All right, so I'll just finish this calculation out to show you that that's true, and then we can just justify that. But that's how we're going to end up picking which CD we're going to have. So I have Reynolds number squared CD equals 4/3, and now I need to calculate this guy right there. So I'm going to pull up Python. Okay, hopefully you can see that. Let me put it up in the corner. It's still annoying. We're covering up our expression. I don't want to make it that big. Okay, and I want G is 9.8, so 9.8 meters per second squared times D cubed, which is 0.076 cubed, divided by nu squared, which is 1.6 times 10 to the negative fifth squared, multiplied by rho 0, which is 1.2, minus rho, which is, or excuse me, rho 0 is 630. 630 minus 1.2 divided by 1.2. All right, and that's my Archimedes number. And if I divide that by 10 to the 10, just to see, that is, let's see, the number is, oops, now I lose my screen. So it's 8.80 or 8.81 times 10 to the 9th. So let me do that. 8.81 times 10 to the 9th. So almost 10 to the 10th. Okay. Now I multiply by 4/3. So multiply by that number by 4/3, and oops, and I multiply that number by 10 to the 9th. And I get back that this guy is 1.17 equals 1.17 times 10 to the 10th Reynolds number CD, Reynolds number squared CD. Okay, so now to find my Reynolds number in this case. So now I'm stuck with my choice that I said earlier. So I say, well, what's that going to be if the Reynolds number is order 10 to the 5? Well, that's going to be something that's a turbulent wake, but a laminar boundary layer. And so we said that was 0.45, or is it 455 or 445? It is 445. So 0.445. So now I can find my Reynolds number is going to be the root of 1.17 times 10 to the 10th divided by 0.445, which I'll plug into my little Python window here, and I'm going to take that divided by 0.445 and all that to the 1/2 power. And now I get the Reynolds number of 1.62 times 10 to the 5th. And if we compare to our previous answer, I think we had 1.64 times 10 to the 5th. So we lost a decimal place that we were being careless with. Okay? So, and then if we wanted to, we could go ahead and calculate U, which, if I remember right from our example in class, U is around 34 meters per second. Okay, so that's the smart guess way, which is basically just to review, you do the same force balance, but now you isolate U and CD on one side and everything else over here, okay, and then you turn that U squared into a Reynolds number squared by dividing by the right numbers, and you end up with something that looks like this. And of course this piece right here with the D cubed, that all fell out because of the the volume over projected area. So if you have a different shape of object, this is going to change, okay? But then once you have that isolated, you have everything that has to do with Reynolds number on one side, and if it's small, then you're going to put something else in for the CD, but if it's big, you know that it's going to be turbulent, and you can put in one of the constant values depending on how big you think it really is going to be. And again, you may need to check and make sure that this is consistent. So at the end of the day, we got a Reynolds number of 1.6 times 10 to the 5, which was consistent with our choice here of using 0.445. So that worked out. Okay, that's all I got for you.